Power in electric circuits. In this video, we'll see how we define power in terms of electrical quantities. We'll also see what equations we use and modify in order to find power in different ways, and we'll apply those equations to various circuits. Remember, when you see the pause video indicator, to pause the video and take great notes. Let's start by reviewing power. Recall from your energy unit that power is the rate of doing work. In other words, the more work you do in a certain amount of time, the more powerful you are. We're going to use this definition of power now to see how we can derive power for electrical systems. So we're going to look at how we can derive power in terms of electrical quantities. Well, power is the amount of work you do in a certain amount of time, and work is related to voltage, and time is related to current. So if you stare at this long enough, you could see that maybe if we multiplied work per charge times charge per time, like we did down here, the charges would cancel, and we'd get back our definition of power, how much work we do in a certain amount of time. So that's how we can define power in electrical terms. We can take the voltage and multiply it by the current. And there is our definition of power. Power is equal to voltage times current. Watts. Watts are what power is measured in, if you recall from our energy unit. So just a reminder that all power is measured in watts. Kind of interesting that James Watt really never had anything to do with power. It's defined a little bit differently though from we had before, and we know that a watt, since it's voltage times current, 1 watt is equal to 1 volt ampere. Now let's take a look at power in a circuit. Here's our circuit down here with our battery, and this battery is doing work and separating the charge and producing the power. So the source in any circuit is what produces the power, and then the current flows easily through a conductor, so no work is being done here, but to push those charges and pull those charges through this sticky resistor over here takes work, and that is where the power is being used. So this power is being produced in the battery, delivered without any work to this point, being used in the resistor, and then the charge cruises back to the battery. So we talk about power being produced or power being delivered. We talk about power being used or power being dissipated. And that's our quick look at the circuit, where the power is produced and the power is used. We can make a couple other equations from our original power equation by using a little bit of algebra here. And so let's say that I know the power being used or dissipated or delivered, and I know the voltage source. I just don't know how much current there is in a circuit. Well, here's our power equation that could help us find the current then. If we divide both sides by the voltage, we can see that current is how much power is delivered divided by the voltage. And likewise, if I started with this original equation, but now I wanted to find out what the voltage was and knew the current, I could divide both sides by the current here, and I could find voltage in terms of power and current. These equations could also be useful every once in a while. Let's look at how we can calculate power in a given circuit. And we'll look at all three of our equations. So we know that our voltage source is 120 volts. That's where we usually plug into the wall. And our current here is 3 amperes. Well, our first way to find power is just simply voltage times current. So using our standard power equation here, and we take 120 volts and multiply it by 3 amperes, and we get 360 watts. Now that we know that, we can work with the other equations to find out really stuff we already know here. But if I knew the power and I knew the voltage, I could find the current, because I is P over V. 360 watts divided by 120 volts gives us back our 3 amperes that we already knew. And finally, voltage is equal to the power divided by the current. 360 watts divided by 3 amperes is 120 volts. So that's how everything plays here as far as the equations are concerned. Remember, it's the source that's delivering the power, and it is the device, in this case simulated by a resistance, that is the appliance or the device that is using the power. So this might be a burner on a stove. This might be a toaster, the heating elements in a toaster. This might be a hair dryer. So whatever uses power, we usually represent or model that as a resistor. So let's see how much you've absorbed so far with a couple of example problems here. Why don't you just try these right from the start without us going through how to do them anymore. So your first question here is, what power is delivered by a 120 volt outlet if 2.5 amperes of current is drawn by the refrigerator? And again, you would model this with a resistor symbol that would model for the resistor, and you could just draw a picture of a simple circuit for your illustration. At the same time, why don't you also do this problem, or after you're done with this one, do this one too before you go on. And now we want to know what current is drawn if we know that the hair dryer uses 480 watts and we have a 120 volt outlet. Give it a try, come back and see how you did. How did you do? Well, let's start with the refrigerator here. Again, we draw our model simple circuit with our source, our ammeter showing amperes, showing the current, and then that's the refrigerator right there as a resistor. Oh, and we've circled and labeled our knowns and unknowns here. Power is what we're trying to find, and 120 volts and 2.5 amperes. And so we list our knowns and unknowns, and P equals V times I would be the equation we would choose. And plugging in 120 volts and 2.5 amperes would tell us that the refrigerator uses 300 watts of power. Now for the hairdryer. Again, we're looking for the current, and we know that the hairdryer uses 480 watts of power, and we have a 120 volt source. So what we don't know is we don't know the current, and we know these two quantities. So I is equal to something with a V and a P, so I is equal to P divided by V. Plugging in the 480 watts and 120 volts, the hairdryer draws 4 amperes of current. And that's how you do problems with power. But wait, there's more. Just one more. One more equation that ends up being quite handy in certain circumstances, and that is, hey, what if I know the resistance and I know the current, and in a particular case I may not know the voltage? Or sometimes it's just easier because we're talking about losses due to resistance in cabling and that kind of thing. So sometimes we just want to use the current and the resistance in order to find power. Well, we can do that because we're going to combine Ohm's law and our power equation. So P is equal to V times I, and V is equal to I times R. That being the case, in place of this V right here, I can plug in an I times R. So over here, well, this V times I is the same thing as I times V. And so right over here, in place of V, I've plugged in I times R. Well, what we see here is we have I times R, so that's I squared times R. So this can be a very powerful equation. Please note it. Well, you've seen how power can be related to electrical quantities, voltage and current. You saw that power is still measured in watts, but now it can be considered as a volt ampere. And you've seen that we can make a whole bunch of equations using our basic power equation. And we can use those to find out how much power is delivered in a circuit by the source and how much power is used in a circuit by an appliance or a component of some sort. And when power is used, we say sometimes when it goes into heating, we say that the power is dissipated in the particular appliance or component like a resistor. So hopefully you grasped all of those ideas. And Scratch's parting comments. And more power to you as you strive for continuous improvement.